So what's that weird eye, the observer, in the Dr. Quantum video you just watched? How can we be sure that we are not interfering with the particles as we observe or measure through which slit each particle goes? How can we be sure we're not interacting with it or disturbing it? I'll show you that this is in fact possible. We're going to observe something without affecting it in any way, and just the act of observing or measuring will change the outcome of the experiment. So let's take a look at an actual setup of this experiment, which is a little bit more complicated. First of all, we have a photon cannon that shoots tiny particles, like in the Dr. Quantum video. However, in this setup, we don't actually shoot these photons at the slit directly, but they first go through a certain crystal. This crystal is called beta barium borate, or BBO for short. The BBO crystal converts the single photon that goes through it into two separate photons. It does that by converting the photon into two lower wavelength photons. Don't worry, if you don't quite understand how this works, that's not actually important for understanding the experiment. You only need to know that one photon gets converted into two photons. So now we have two photons which go off into two different directions. We'll call them direction A and direction B. We'll also put a detector in each of these directions, detector A and detector B. These are similar to the screen on which you saw the interference pattern in the previous video. With these detectors, we can tell when a particle has landed. The two detectors are hooked up to a so-called coincidence counter, which I'll explain further in a second. Now we'll introduce the actual double slit into the experiment, which we'll put in the way of the A photon. As you can see, we're not putting a double slit in the B direction. The photons just go straight towards the detector. Now, when we run the experiment, the photon cannon shoots particles at the BBO crystal. They get converted into two particles. One goes through the double slit and into the A detector. The coincidence counter goes click and waits until the B particle also arrives at its detector. When both particles have arrived, the coincidence counter goes up by 1. We're going to show these so-called coincidences on an axis. Now we'll leave this running for a set amount of time, say 400 seconds, and keep counting the coincidences whenever both photons hit the detectors. 1, 2, 3, and so on. Now sometimes it can happen that a photon doesn't actually hit the detector because it gets diverted by the double slit, and instead it zooms by the detector. Since these photons are not detected, we're also not going to count them. We can only count the ones that actually hit the detectors. We'll also write down the position of the detector, and we'll say that the detector is at position 0 when it is right in the middle of the double slit, just like in the diagram right now. Also, these numbers here aren't quite right. This was just for illustration purposes. In reality, the final count of coincidences will be much higher. After the 400 seconds, we'll move the detector to the right by a set amount, let's say 1 millimeter. We'll run the same experiment again for the same amount of time, 400 seconds, and keep counting the particles, and also write down the final count in our diagram. This time, fewer particles will hit the detector, since it isn't in the middle anymore. We'll keep repeating this process a few times. And we'll also do the same thing again, but this time moving the detector in the other direction. After we're done, we can connect all the points in the diagram and we'll get this graph. Of course, this is just a simplified version of this graph. Here's one from an actual experiment. If you look closely, you can see that this graph looks similar to the interference pattern that was shown on the screen in the Dr. Quantum video. This is because when the detector is in the middle, most of the photons will hit it, whereas when it is off to the side, more photons will just zoom by and not trigger the detector. It is really strange, though, that this pattern emerges, since the single particle that goes through the slit is behaving like a wave and not like a particle. If it was behaving like a particle, we'd expecting a graph that looks more like this. Keep in mind that with the current setup, we have no way of telling through which slit each photon goes. I also haven't explained yet why we need the B side of the experiment. By the way, you can recreate this part of the experiment very easily at home and actually see the interference pattern firsthand. All you need is a laser pointer and some tinfoil. See the link in the video description for instructions. In the next video in this series, I'll explain how we can actually observe through which slit each particle goes. I'll also show that we're not actually affecting the particle with our observation in any way.